So I will speak about kind of my mathematical adventure last year with Yuri Chinkel. It really came from as accident, and I hope you will enjoy it. Yeah, so I will start with the following very brief introduction to birational algebraic geometry. In fact, one can trace it back to this most important theorem in mathematics, Pythagoras theorem. You know, x squared plus y squared equals z squared gives you three sides of rectangular triangle. It's very useful in agriculture, because in agriculture you should be to keep track of your fields will be rectangular to calculate the area, and this is a way to make rectangles. And there is a simplest solution, which everybody knows. It's 16 plus 9 is 25. So you have 12 pieces of some rope of equal size. Then you can carry in your pocket a tool making perfect right angle. Of course, it's Pythagoras theorem, but it was known to other civilizations, and this 3, 4, 5 were one can find in many artifacts. But then people discovered that there are other solutions, like 25 plus 144 is 169, and these numbers I don't even can pronounce. Yeah, so there are infinitely many what's called Pythagorean triples. 3 integers, so the sum of squares of 2 is equal to square of another. And the general solution, it also was known to Greeks. You take just 2 arbitrary numbers, a and b, one even, another odd, and you take a squared minus b squared, another 2ab, another a squared plus b squared, and you use this remarkable identity, like 3 plus 5. If you take, for example, like 2 and 1, you get 2 squared minus 1 squared is 3, 2 times 2 times 1 is 4, and 2 squared plus 1 squared is 5. Yeah, so and so on. Yeah, so that's an old description of all Pythagorean triples. And what does it mean? When you consider polynomial equations, like sum of squares or products of some variables, you do algebraic geometry. And the equation which for Pythagorean triples, it's homogeneous equation. So if you have squares of each variables appears only, and if you rescale variables by constant, multiply by 100 or 3, whatever, you get another solution. So if you have one solution, you just can multiply by some number and get another solution. So that says that your equations are homogeneous. And now we can try to solve equations. For Pythagorean triples, we solve equations in integer numbers. But after rescaling, it's the same as that we solve in rational numbers, because if we have some common denominators, we multiply by the denominator, get integer numbers. And rational numbers form a field. It's something where you can divide and multiply, and it can divide by non-zero element. And there are other fields: real numbers, complex numbers, finite field, etc. And what we do here, we consider a curve in projective plane given by this equation, and we treat variables up to rescaling, and we introduce only triples of variables which are not simultaneously equal to 0. Yeah, so it's like you take 3-dimensional space, remove 0, and then rescale, you get, naively you get sphere, but because we also multiply by -1, you divide by inversion, you get projective plane. And so abstractly, from point of view of algebraic geometry, this equation gives you a curve in a projective plane. And what does it mean that you can write all solutions? It means that this curve is a rational curve, so it can be identified with something with one variable, projective line. And the correspondence is given by the following formula. Actually, if you go back to this a squared plus b, divide, for example, all 3 coordinates by the third one, then you get these 2 expressions. T squared minus 1 divided by t squared plus 1 and 2t times t squared plus 1. These are 2 points whose sum of squares is equal to 1. And what I draw here is how geometrically this correspondence look like. You have a circle. Circle is given by equation sum of squares is equal to 1. It's just our Pythagoras theorem at the end of the day. And now to point on the circle, you want to associate just one number. And how I associate it, you pick a point on a circle just on the left corner and draw a straight line through another point on a circle, intersect with vertical line. And if my circle is given by equation sum of squares coordinates equal to 1, then the vertical line it will be 1, and horizontal coordinate and vertical coordinate will be 2 times t. Yeah, so it's a geometric way to say these formulas. One can in algebraic geometry, it's kind of language between pictures and formulas. So it's and instead of writing formulas, you can draw this picture. Okay. And so in birational geometry, it's something about birational equivalence. It's not just means it's one algebraic variety is another, but it's some kind of weaker equivalence. And the definition is the following. You consider smooth algebraic varieties. It's something given by system equations, either homogeneous or inhomogeneous. One's called affine, another's called projective. And at each point, the variety locally looks like a flat space, so it means smooth. And suppose we have same dimension and defined by equation with this coefficients is the same field k. So like rational numbers or real numbers. And they're called birational equivalent if the following holds. And still, algebraic geometry, it's algebraic and geometry. There are kind of two languages. One can use one or another, and every notion one can express one way or another. In algebraic way, we say the following. If we have algebraic varieties, one can consider we can make a huge field, what's called rational functions. So it means that you consider all possible kind of algebraic expressions which maybe sometimes don't have meaning, but at generic point have unique meaning, and kind of ratios of two polynomials roughly. And such things form a fields, and you say that varieties are birational equivalent if these two huge fields are isomorphic. So one can make one-to-one correspondence, but of course one can there is some kind of field of constants, and one should make a correspondence which respects these fields of constants. Yeah, so this is geometric definition, and there is a geometric definition. When you don't write any formulas, you don't speak about algebras at all. So what you do, you have your algebraic varieties, some set of solutions of some equations, and you have another algebraic variety, x2, it's a solution of another system of equations in other variables. And what you do, you remove from this variety some pieces of which are called divisors in algebraic geometry, or it's kind of hypersurface, something of codimension 1. So don't touch general point. So remove something of strictly smaller dimension. If you remove something of strictly smaller dimension, you get things which you can identify algebraically. Yeah, so it's completely different description, but it's equivalent notion, and this means that varieties are algebraic, birational. And variety called rational if it's birational equivalent to projective space. So it means that one can introduce coordinates at generic point outside of some divisor. And algebraic geometry studies what are which varieties are rational or which are birational equivalent to each other, and that's sorts of questions. And now, how you make algebraic varieties? You have many variables, and you write some system equation. Let's record one equation, not a system equation, just one equation, and you'll get interesting in homogeneous equations. Inhomogeneous one can replace by homogeneous. So we consider hypersurfaces in a projective space, many variables up to rescaling, and given some equation of degree 2, like sum of squares or maybe some mixed terms. These are called quadrics. And if you consider quadrics in projective space of arbitrary dimensions, And if your field is algebraically closed, so it means that all algebraic equations have solution, like complex numbers. So real numbers or rational numbers are not good. But for complex numbers, situation is much simpler. Then all these quadrics are rational. So from points of view birational geometry, they are all the same. And the proof, you use something called high-dimensional stereographic projection. Maybe I'll go back to some few slides. It's essentially like this picture which I drew. I have a circle and a tangent line, and take a point on the circle and project my circle to a line. And the same can do with a sphere. I make a huge sphere, take tangent plane and project from point sphere to the plane. Then identify sphere and a plane birationally, because you see, like in this correspondence, if you ask yourself what corresponds to this thick point from which I emanate my rays, it will be some point in infinity, but you don't know which one. It can get some ambiguity. Yeah. But there was this word which I emphasized that the field should be algebraically closed, so it should all polynomial equations should have a solution. And it's really important condition, because if it's not true, then the picture is much more complicated. For example, we consider real numbers instead of complex numbers. And write equation in homogeneous coordinates, let's say, sum of squares is equal to 0. In inhomogeneous coordinates, you just divide by 1. You say that 1 plus sum of squares is equal to 0. Definitely cannot, especially the second equation, cannot solve in real numbers, because squares are all positive, and sum of squares is positive. So this equation doesn't have any solution at all in real numbers. And if your field is infinite and you have varieties rational, that have infinitely many points. Yeah, so it's definitely not a rational variety of real numbers. Yeah, so in birational algebraic geometry, one should kind of really take care of a variety of which field, algebraic close or non-algebraic close. So it's simpler of algebraic close, and when it's not algebraic close, it's more arithmetic type of problems. Okay, so now we kind of understand quadratic equations. What about equations of degree 3? This, the story about cubic equations is much more complicated, because first of all, they could be very singular varieties given by cubic equations, and there's really no good picture about it. But if you consider varieties which are smoothes without any singularities, and again, all algebraic closed fields, then the situation is the following. If you consider one-dimensional variety, so it means that, like, you take in inhomogeneous coordinates, you take two variables and one equation. Like you take kind of obvious generalization of this equation for Pythagorean triples, or we can take sign, like sum of two cubes equal to 1 or minus 1. This thing has really few solutions for rational numbers, and one cannot, it's not rational variety by many reasons. It's if, for example, consider the complex curve, there's a torus, it's not a sphere. So one cannot parameterize, one needs some elliptic functions. And this gives elliptic curve. So it's definitely not rational in dimension 1. In dimension, oops, it's misprint. In dimension 2, it's second point should be dimension 2, so it was misprint. In dimension 2, consider a cubic surface in P3, it's rational, and it's P2 is blown up at 6 point. I will explain later what does mean blown up. It's kind of replace point by a projective line here. Yeah, so it's a very famous surface. If you consider cubic surface in P3, it's contained 27 lines, and it was one of kind of most studied objects in algebraic geometry. Now we go to next dimension, like you take 4 variables and take whatever, and you get there are many three-dimensional varieties, three-dimensional cubics, but which when they are smooth, they are never rational. It was a great result in '72, proven by Clemens and Griffiths. And then we can go further. Dimension 4. I will stop here. In dimension 4, the situation is very obscure, I have to say. When you count how many parameters for different cubic equations up to change of coordinates, you get 20 parameters. It's huge 20-dimensional space, parameter space. And it seems that it has a dense collection, everywhere dense collection in all sense, like in complex numbers, of 19-dimensional hypersurfaces in parameter space. So it means that you get some equations relating these 20 parameters for equation for cubic, when the things became suddenly rational. And the formula should be enormous, how to parameterize it. I'm afraid it's even the simplest formula takes several pages, how to parameterize it. But what is expected is that if consider very, very general cubic with no relation between coefficients, some random transcendental numbers, then it will be not rational. Yeah, so you get kind of really mixture of behavior. It's neither always rational, neither always non-rational, and it jumps from one to another. And it's one of the biggest open problem in the area. And I want to make kind of small announcement, which is not yet finished work, but hope maybe next year it will be finished. It's work with project with Ludmila Katsarkov and Tony Pantev, that we hope we will prove this conjecture. And using really kind of great mix of various ideas coming from Gromov-Witten invariance, which is related to mirror symmetry, and I'm here actually came as a member of Simon's collaboration on homological mirror symmetry. We'll have a meeting tomorrow. Yeah, so this will be really appropriate to speak about this topic for me, but unfortunately the thing is not yet finished. Yeah, so it's still under investigation. Yeah, so it's related to story coming from Gromov-Witten invariance, but also hot structures, motifs, and classical birational classification of surfaces known to in Italian school. Yeah, so it's really kind of really should be a nice mix of all ideas in algebraic geometry, but it's really for future work. And I have to say that there was interaction between like mirror symmetry, Gromov-Witten invariance, and equation of birational geometry before. In the early days of mirror symmetry, one of pioneers, Viktor Batarev, invented to prove that of the fact, kind of, he was inspired by mirror symmetry, that two birational equivalent Calabi-Yau varieties, which have volume elements, no vanishing volume elements, have the same cohomology. And his idea was using periodic integrals, and I generalized it to something called motivic integrals, which became some kind of industry here. But it's not really directly mirror symmetry. And last year, one of participants of our meeting, McLean, found a remarkable purely analytic proof using symplectic topology of this algebraic fact. Yeah, so things are starting to really talk to each other. Okay, so birational algebraic geometry is really fascinating and difficult subject, and one needs it's kind of this very bizarre logical steps and connections and many different ideas. It's not really a tamed subject. There are very, very different approaches here. And the real topic of my talks, it will be, again, some work on algebraic geometry, which we have done last year with Yuri Chinkin and my colleague from HS, Vasily Pistun. We constructed new birational invariance of algebraic varieties endowed with induction of a cyclic group. It's not yet related to mirror symmetry, but it's one should say no to this question, because it looks that eventually all mathematics will be related to mirror symmetry. That's my deep hope. Yeah, what is all this about? in algebraic geometry, not birational geometry, one preferred to work with something called smooth projective algebraic varieties. So it means, what does it mean? You have projective space, like homogeneous coordinates, and you get some system of equations which define a subset which is, each point has no singularities. And it will be compact because projective space is compact. So mathematicians in general like smooth, compact things, and algebraic geometry is especially, and they're suitable for topological and cohomological methods. So if you don't have something not smooth compact, you want to do it, make it smooth and compact, and then you start to work with this. And to deal with singularity, one this principal tool is a resolution of singularities in zero characteristic by Hironaka. It was a really kind of main tool or axiom in algebraic geometry because not many people studied the proof. I definitely didn't study the proof, so I use it like everybody, almost everybody, as an axiom. And then there was about 20 years ago some generalization of this called weak factorization theorem, which gives a total control of how we do with one resolution, another resolution. And this weak factorization theorem implies that the following fact: how we reduce the equation of birational geometry to equations about smooth projective varieties. You consider birational types of varieties of given dimension over some field of characteristic zero, because everything is based on resolution of singularities. And how to describe this world? And the claim is the same as a set of equivalence classes of the following thing. You consider smooth projective connected algebraic varieties over the same field, and you generate equivalence relation by the following simple thing. You have your variety, X. Now you have a smooth closed subvariety Y, which should have smaller dimension, but smaller at least by 2. Divisors are not play no role here, so it should be like point in 3-dimensional space or curve in 3-dimensional space. And you make a BlowUp. Yeah, so the same BlowUp which I mentioned a couple of times before. What is a BlowUp? So the basic situation to understand is a BlowUp of a variety which is not even compact but still smooth. You have a vector space. You have a vector space. It's also a algebraic variety given by no equations in homogeneous variables. And you get subvariety which is a point, 0, in a vector space. What is a BlowUp of vector space at 0? You consider pairs of line and a vector sitting on this line. Such thing you can see in 2 ways. You just first choose line arbitrary passing through 0 and then arbitrary choose a point. So it obviously sees it's a smooth variety. You don't see any singularities. But also the things, oops, sorry, there's still misprints everywhere. There is a projection from this variety. It should be pi, not 2 pi, and pi is not 3.14, but just Greek letter. From the BlowUp to vector space itself, you forget about line. And in this way, something funny happens. If the vector is non-zero, it's uniquely determined the line, because you can pass unique lines from 0 and any other point. But is V 0, you just you can choose arbitrary. And in general, if you get a smooth closed subvariety in a smooth variety, then there is something absolutely canonical, this BlowUp, and you have a map from this BlowUp to X. And it has few basic properties. So it's a new variety, and the map is epimorphic. So each point comes from at least one point in the BlowUp. And if point doesn't lie in your submanifold, you just get only one. It's come from essentially the same point, kind of the same point in BlowUp. But if it's a point on your subvariety, then the fiber the set of points which maps to this point is a projective space of dimension n minus m minus 1, where n is dimension of x and m is dimension of y. And here you see why it's really important to have codimension 2, because otherwise you get kind of a negative number. Then this BlowUp guy is smooth, and the preimage of your thing we make BlowUp turns out to be, because it has divisors, have dimension n minus 1. How we calculate it? Because the dimension of fiber is n minus m minus 1, but now you should add dimension of the running point on y at m, you get n minus 1, so you get really smooth hypersurface. And this it turns out that this guy is projective if your varieties, original varieties was projective. Yeah, so it's something really something nice which you can do with smooth projective varieties. You make smooth projective variety, you make smooth subvariety, which is again smooth projective. You make BlowUp, you get another smooth projective varieties. And device also will be smooth projective. So it's all will be word something about smooth projective varieties in this word. And as I explained, through this BlowUps, one can reformulate equation of birational geometry, which about complicated fractions, to some geometric equation about this very nice smooth projective things. Now I'll go to this topic of new equivariant birational variants. What does it mean, equivariant? It's some kind of version of algebraic geometry when you get some situation with certain symmetry. It's imitate kind of Galois symmetry in like non-algebraically closed fields. So you have a finite group. For example, you have a transformation which is periodic of certain period 5, or later we'll see period 43, for example. This should be very interesting. Yeah, so what have some finite group of symmetries and consider birational maps between varieties which commute with G action. And there are applications, but by Andrew Kresh and Yuri Chinkel to orbifolds, and I hope there will be some fuzz applications to this subject. And yeah, so it's some kind of version of birational geometry. And this weak factorization theorem, which was the main tool to control, to translate from equation about complicated fractions to questions about geometry without formulas, also works in equivariant setting. So, and when consider varieties with section of a group, a field of characteristic 0, and interested in equivariant birational equivalence, it's the same as you consider smooth projective algebraic varieties on which group acts. And what you do, you model by equivalence relation when you make BlowUp at, again, smooth subvariety which are preserved by the action of the group. As I told you, it's much easier in algebraic geometry to work in all algebraically closed fields and characteristic 0, and the best field which you know is complex numbers. So let's say the field is complex numbers, and the group is should be commutative, and just to simplify the life, it will be cyclic group. So just get one element of order n acting on your variety. Yeah. So what happens now? Suppose I have this group, like cyclic group, acting on my variety and generically acts freely. So the stabilizers of you kind of randomly chosen point will be trivial. Then I get some fixed locus set of points which are fixed by all elements of my groups. If it's cyclic group, just fixed by given transformation, and it's automatically smooth, actually projective subvarieties. Actually, it could be not one of them. It could be several subvarieties. They can have different dimensions, but they do not intersect. Now, for each connected component called algebraic geometry, reducible component of the fixed point locus, just pick a point. And if you get action of the group or fixing this point, then it acts on the tangent space, because near the space, the main property of the smooth variety is that near each point looks like a vector space. Yeah, so it looks like a tangent space. And you get action on the tangent space, which is n-dimensional vector space or your field, and you get what's called the representation of the group. So for each element of the group you have corresponding automorphism, and because the group is abelian, it should be some of one-dimensional irreducible representations, which is called characters, and just homomorphism from the group to C star, which is again cyclic group. And you get for each fixed point, which you put on each component, just collection of n characters. But you don't know which is first, which is second. So they're defined up to permutation. And now, the idea is just to associate certain weight, which is denoted by some to each component, which should depends only on this collection of characters. It will be a certain symbol or weight. Eventually, it could be some number. And this thing should satisfy certain relations, which will guarantee that anti-relation should choose in such ways that the things will be invariant under blowups. Yeah, so it was some kind of very naive abstract idea just to construct invariance. When we started to think about it, we have no idea, we didn't, just kind of random shot. We have no idea whether such thing exists or what is going on. It was kind of very naive first approximation to make it an invariant. And in order to make it invariant, one should check that if you make a blowup in this under invariant manifold, the things doesn't change it. It will give certain system of constraints. What are these constraints? Yeah, first of all, these symbols they correspond to collection of n elements in your characters, and this collection should, if you spend subgroup in this finite group, like cyclic group, it should be the whole group of characters. It corresponds to the fact that my group acts generically freely. Okay, so you get this like coprime numbers from condition, and there are two relations. One is pretty simple. It's called denoted by S, but from symmetry. If you make any permutation of indices, you get the same expression. It just reflects the fact that when we associate this symbol to a fixed point, we make this choice of ordering of these characters completely arbitrary. So the things shouldn't depend on this choice. And the second is kind of pretty complicated relation, which we came to analyzing very situation about this kind of looking how this invariant subspaces, tangent subvarieties, and so on. It's called B because it's relative birational geometry. It says the following: you take, you decompose your set of points, characters in two groups of k and n minus k elements. I think it's k related to codimension of the space when you make blowup. It should be at least 2. And so first k denoted by a1k, but the rest chain notation denoted by b1 by n minus k. So that will be things which generate a symbol. And the axiom says the following, that this symbol is sum of other symbols, and how you do? You take among these a's, pick some value ai, remove it from all other elements in group A, but don't do anything with group B. And there's kind of really unpleasant part here, which I make it in red. You, for example, if you make ordering, if some character here appears like some 2 or 3 times, you pick only the first one of them. So from example, you pick the first one in the ordering, and it's combinatorial. It's very, very unpleasant thing. Yeah, but still we get some system equation and want to write this relation. Yeah, that's then we get some finite integrated group, and we can solve the system equation in like rational numbers or residues modulo. some integer, and get invariance. Yeah, so this, as I explained, this relation symmetry guarantees that it things doesn't depend. If I get my concrete smooth projective model, G-covariant model, I get well-defined thing because the ambiguity was ordering of these characters. But this B really shows that these things it doesn't change on the blow-up. It's really, you study 3-4 different cases and get the system of equations. Yeah, essentially the main interesting point, the main kind of interesting situation when you get one isolated fixed point and all characters are distinct. Then if you make blow-up, you get n new points, and it will be a version of this relation which I drew before. Yeah, so that's a kind of very naive idea. For example, this fixed point subvarieties could be not zero dimension, could be high dimensions. They have some interesting algebraic geometry, but I completely ignore this all details. I kind of pretend that it plays no role. In principle, one can add this data. Yeah, so it really was kind of first approximation to more delicate invariance. And here we just keep very rough data, how many connected components. Yeah, so it was, again, things from which a priori it's not clear whether it will give something interesting or not. And the equations were so ugly that it was natural instinct to replace by something better. I mentioned that in this relation, when several components of this symbol coincide with each other, you just treat them some kind of in strange way. And it's much better to mathematical instinct says that it's better to write different relations without such thing. So we kind of just ad hoc defined a new thing. We replace square bracket by this angle bracket and make the same relation as before. And here, just in the second relation, I don't put this red kind of special cases, nothing. So it will be much easier, for example, to program on computer. It's also one of the why its function. This thing is better, and it really looks nicer. Yeah, and it turns out. And I played with a more complicated group, easier group, and turns out that they're almost the same. And that gives us idea that probably they're related. And in fact, we proved it. One can map more ugly group coming from birational geometry to this nicer group M by the very simple formula. If I get my symbol when all entries are not zero, I just map to the same symbol with angle bracket. If I get only one zero, then I take twice. And if I get two zero or more, then it should map to zero. Yeah, so it's by kind of trial error we came to this formula. And the theorem is it's well defined, and its rejection up to kind of elements of order 2. And that looks kind of simple theorem, but when we wrote a complete proof, it took something like 3 or 4 pages, about 14 different cases, very complicated tree of logic. Yeah, but eventually it all works. And conjecture, we still don't know how to prove that it's isomorphism model torsion. It's reduced to some nice explicit identity, which computer checks, but again, we do not know how to prove it. But basically, if you're interested like solution of equations in rational numbers or complex numbers, this thing says that there's no difference between ugly relations and nice relations. And now then we started to calculate. Yeah, so we consider cyclic groups, and as I told you, this computer experiment shows that up to torsions they're the same, and what you get some number of independent invariants for the section of cyclic groups on surfaces on three-dimensional manifolds. And here is this table which I showed for small n. You see it like looks at number of invariants for in 3 dimensions much smaller, but then we go to very big orders of cyclic groups. It started to compete with order of 2. So sometimes larger, sometimes smaller. Yeah, now I think we have really good understanding. So get this big table which took many hours and days and weeks maybe. But when we go to dimension 4, we get very, very little. So the first non-trivial invariant appears for a cyclic group of order 27. And if you go to 5, I think we get only one number for 81. And this calculation really took really long time. So there's something funny here. You see this 27 3 to the power 3 is the first number for which you get invariant in dimension 4. And for dimension 5 is 81, which is 3 to the power 5. And you go back, you see, I think you see this in dimension to the first invariant appearing in cyclic group order 3, and here it's order 9. All powers of 3. Yeah, so that was kind of wilderness. How we calculated it? Yeah, so originally I was doing experiments on just my computer or smartphone using Sage. But then Yuri has good connection just across the road with Flatiron Institute, and Alex Barnett and Nick Carrera. Hope I will meet them today. They help with the expertise in the powerful machines. They have some kind of free time and calculated, crunch our numbers. But it also became kind of, at some point, very slow. Oh, next number we should expect in 24 hours. Oh, and then it's maybe 2 days. Yeah, so it was really start to grow very, very slow. But then they discovered on the web some pretty recent software written by something like 3 years ago called SPASM, sparse matrices, something like this, and which was written by 2 kind of essentially like postdocs in France, and which works 100 times faster. Yeah, so it was when they discovered this, okay, said, forget our machines, we can do it yourself. Yeah. But with these calculations, if you want to really understand such, you start to calculate more and more. You still kind of always can reach the limit of possible. And then there was something really funny thing happened. At IHS, there was some physics conference, and my former colleague, who's now in Simon Center of Geometry and Physics in Stony Brook, Nikita Nekrasov, gave some talk about his work on gauge theory. And in the end of his talk, he showed some identity for some partition functions, and it was again BlowUps. And those formulas was really exactly like our relations for symbols. And after the talk, I came to him and said, that it's strange. We have really the same mathematics here. And another colleague of my physics colleague who replaced Nikita at IHS, Vasily Piston, kind of also stayed around, and he got really interested in it. And he joined our team. It completely changed the perspective. First of all, he's a very good programmer. He optimized even the SPASM program, which was in C, and then optimized the input, and it started to run again maybe 10 times faster. Yeah, so it became incredibly fast. And he had in his office computer with 400 cores, but it turns out that in Hinge there's only 1 core. It's not necessary to make this multi-core. I think the main problem is just to fit this program with the data. And data was really huge, of size of, I don't know, how many terabytes. It was really enormous things to do it kind of in a personal computer, but it really works like this. And we went to really incredible sizes of calculation with this Spasm program. They're essentially very close to what is called records in RSA algorithms. You know, like in banking, everybody's based on product of two prime numbers, and who can decompose like 200 numbers with 220 digits in product of prime numbers will be a good guy. And this was some last record, something like 5 years ago, and I read description. It reduced to essentially to find solving overdetermined system of equations over finite field, mod 2. And the parameters are very, very close to what we get on our PCs. Yeah, so probably we can, if we try, we can beat the next record with this Spasm. I think it's really great program, and we are sure that it works correctly because nobody checked it, but the result is so convincing that we kind of know that it's correct. And Vasily Pistun, he's really physicist. He started kind of to play with numbers to see these dimensions and get more and more data, and he makes some observations, some predictions of certain algebra structure. And for example, this thing we want to get this powers of 3 followed from his picture. And recently with Yuri we proved his conjectures, which he made. So it's kind of really clean picture. So the whole story turns out to be related to really kind of mainstream mathematics, but of different nature. So it's called modular symbols. So I now really wrote you relations in a clean form, like for n equal 2, for this beta symbols, the relations look like this. You get A and B, which generate your cyclic group, say, and you put the relation AB is equal to BA and is equal to sum of two guys. And if you consider cyclic group of some prime order P, which is at least 5, then one can calculate about B group we don't really know, but for M group we know, and we get P squared plus 23 over 24, which is 1 plus simple number P squared minus 1 over 24. And what is nice about this P squared minus 1 over 24? It is integer number, is P prime starting from 5. And it is a genus, a kind of number of handles of what's called modular curve. It's a kind of one of main object in many domains of mathematics and modular forms. It's the following. You consider upper half plane. So this funny letter is imaginary numbers. You get. Oops, sorry. There's so many misprint here. I'm afraid. Yeah, I don't know how it appears. So you get a point in a complex numbers with imaginary part and this action of fractional linear transformation over 2 by 2 matrices, and consider the group of 2 by 2 matrices which are equal to this upper modular n. You get one unknown entry, otherwise 1, 0, 0, 1. And the genus of this modular curve, it's some number which you know explicitly, but the formula is pretty complicated. It's roughly this n squared minus 1 over 24, but plus some small corrections. And the conjecture, which we still don't know how to prove, but it said that its dimensions of these two groups is a genus n plus sum of over divisors 5d, 5n over d. Phi is this earlier 13 functions. It's for each integer. Count how many smaller numbers which are coprime to this integer. So you get this formula. But there is a nicer part of this whole story. It's called odd part of the group, and it's really related to mainstream mathematics. Namely, we just add one extra relation, that these symbols are anti-symmetric in each letter. I said it's anti-symmetric in first letter, but because it's all letters play absolutely equal role, I can just impose it just on the first letter. And I get a smaller group, mn minus. And the theorem kind of, the day turns out to be almost a tautology, said that this group is something which you can express mathematically in this way. You consider subgroup of J ln Z, not S ln Z, but J ln Z, which should be a bit careful here. And this group is a subgroup of finite integers of group of matrices which stabilize some epimorphism from lattice to your abelian group G, not necessarily cyclic. So you get this kind of congruent subgroup, and you consider cohomology of this group with coefficients in one-dimensional model. You consider model of determinant or orientation and raised to nth power. So for even n, it will be trivial coefficients. Yeah, so that's the thing. It's when you calculate cohomology of this group with coefficients actually in any fine-dimensional model, it will be all cohomology will vanish above this degree. So it's the last degree when you get non-trivial cohomology. And cohomology, it's usually kernel divided by image. But if it's last degree, it's something divided only by image. You don't make calculate kernel, so it will be like much simpler to work with. This cohomology at extreme degrees. And there was an old story started by Yuri Manin in 60s for dimension 2, and then Barry Mazur for general n. Avner Ash worked on it for 30 years. So they have people have some machinery, and these relations, it's at the end of the day, if you take this mn minus, it will be basically the same object. Yeah, so it will be tautologically the same thing. But without this quotient, it kind of seems to be more interesting extension, and there is some interesting thing goes on. Think without quotient. And for this mn minus, yeah, so Vasily Pistun didn't know anything like this, so he discovered it by himself, that it's necessary to make this negative part and make a lot of observations, and he proposed to consider this negative part. And he proposed some idea about making some products and coproduct, but it's not Hopf algebra, it's kind of more tricky thing, each relating various n's and g. In fact, this relations of products or coproducts seems to be have the same logic as in certain other thing which we have done with Jan Soebelman about 10 years ago, something called cohomological whole algebras, and also have very closely related things in completely different contexts. And for these products and coproduct, one can define primitive parts, so it means it's something which cannot be reduced to smaller values of dimension or smaller group. And Pistun conjectured some kind of iterative picture, and with Yuri we kind of make a proof which was pretty elementary but pretty tricky. And so this negative part is expressed through some primitive part. Namely, you decompose dimension of your varieties is a sum of non-negative integers, positive integers, and order of cyclic group is a product of integers, and you take, I forgot to write, entries. This mn's should be of z of capital N. And something similar but a bit more complicated works of things without minus. Yeah, so it's everything reduced to this primitive part. And what is this primitive part? Yeah, this primitive part it seems to exist only in dimensions 1, 2, and 3, so nothing in dimension 4. And it seems to coincide with the most interesting part of cohomology, it's called cuspidal part. And dimensions are kind of uncontrolled for n equal 1. For n equal 1, you get this Euler function divided by 2. And for dimension 2, it's a very classical series of modular forms. You get these numbers, which grow essentially like n squared or 24, and there is explicit formulas I explained to you. But for n equals 3, you get something really growing very, very slowly, maybe like logarithm. And this 43 was something which I observed still on my laptop. And for this, there's no formulas. It's like slowly growing random numbers. And the whole thing is controlled by a very, very small table, which one can really make half of page of numbers. Before we get many, many pages of numbers and very unvalued information, but now it's organized in very, very clean data. And because it's, I don't know, something like 10,000 numbers are coming to this whole thing, it's, I think, a good sign that the Spasm program is absolutely correct. And so you see that it was kind of really fascinating journey. We started with equation of algebraic geometry, make some very naive kind of first combinatorial ansatz, and then led to deepest questions in number theory. And we communicated with people in automorphic forms. This decomposition in this sum of tensor products seems to be a new result which they like. But we are not specialists, so I cannot say anything more. Thank you.